Over the Aleutian weather front, a fuel gauge approaching empty narrowed the final flight of Consolidated B-24D Liberator serial number 41-23908 into a hard operational boundary. No safe runway, no normal recovery, and no time to keep searching. Operating with the 21st Bombardment Squadron, the immediate tactical objective was keeping the crew alive under severe weather limitations. Decades later, the stakes would shift to extracting a structurally viable heavy bomber from the Aleutian Tundra. On January 18, 1943, the bomber launched with a designated mission targeting maritime traffic near Kiska. The Consolidated aircraft was a heavy, strategic bomber built for endurance, with 4 engines, a massive wingspan, and little tolerance for blind, low-level recovery. In the Aleutian theater, operational limits were dictated entirely by atmospheric instability rather than enemy action. Barometric pressure gradients shift rapidly across this island chain, creating localized weather systems that blind flight crews and shut down visual navigation. Before the Liberator could reach the assigned target zone, severe weather blocked the route and forced the crew back toward Adak, where fuel management and runway access became the next limit. Instead, the weather system worsened across their return vector. Back over Adak, visibility was so poor that the formation could only circle and search for a break in the weather. One B-24 managed to land, another crashed into parked P-38s, and the remaining aircraft were forced to disperse. Every minute spent searching for an open approach path consumed the margin that remained. Pruett's bomber could no longer stay over Adak or search safely for another field beneath the storm layer, forcing the crew into emergency alternatives. Captain Ernest Pruett evaluated the remaining options as the fuel banks ran dry. A sea landing failed the mechanical test. The B-24's high wing, deep fuselage, and long bomb bay area would likely convert water impact into breakup and rapid flooding. The only viable choice was a controlled forced landing on solid ground, despite the lack of normal visual references. The crew identified the general vicinity of Great Sitkin Island through the storm. Pruett committed to a gear uplanding on the unseen terrain. Keeping the landing gear retracted was a deliberate mechanical calculation. Lowering the heavy main gear would cause the wheels to dig into the uneven ground upon contact. This would force the aircraft to flip forward, resulting in a catastrophic structural breakup and heavy crew casualties. A belly landing kept the center of gravity low and prevented the airframe from catching a hard edge. The pilots descended through the zero visibility ceiling, committing the heavy bomber to the ground. The Liberator made contact with the island. All crew members survived the forced landing and awaited rescue. The machine itself, however, was permanently immobilized. Stripped of flight capability and resting inland from the coast, the airframe transitioned from an active military asset to a static piece of evidence. The remote coordinates and harsh climate made wartime salvage impractical, so the military extracted the personnel and left the heavy bomber where it stopped, initiating roughly a half-century of in-situ exposure. Aleutian winds, cold maritime moisture, fog, rain, and salt-laden air began a long-term test of the aluminum alloys and internal bulkheads. How did the aircraft survive a forced landing on rough volcanic terrain without catastrophic fragmentation? An approach vector crossing directly over a 50-foot coastal cliff established a strict geometric limit for the descending bomber. Clearing this coastal obstacle required the pilot to maintain sufficient airspeed to avoid a stall, while preparing to arrest forward momentum immediately upon crossing the land boundary. Arriving over Great Sitkin Island at minimum altitude, Ernest Pruett held the wings level. A dropped wingtip could strike the ground first, creating a violent rotational pivot that could tear the heavy wings from the center section. The control inputs forced a linear touchdown alignment, dropping the flat lower fuselage onto the interior surface of the island. The immediate physical decision was to trade forward velocity for a controlled ground slide. When the metal skin made contact, the specific topography of the island helped manage the energy transfer. The heavy fuselage contacted mud and wet tundra grass rather than a continuous field of exposed rock. The B-24 slid about 1,000 feet before stopping, narrowly missing several large boulders at the foot of the volcano. That configuration turned the wet tundra into a braking surface rather than a pivot point. The slide dissipated enough energy to keep the central compartments from collapsing. By bleeding off velocity across the ground slide, the forward sections avoided total catastrophic compression. The airframe still suffered crash damage, but the central crew area remained intact enough for the men inside to live through the deceleration. The injury pattern made the margin measurable. 7 crew members avoided major injury, while bombardier Holiel Askell suffered a broken pelvis and had to be carried from the aircraft. The crew then improvised shelter and signaling. The intact aluminum shell settled deep into the tundra vegetation. Without maintenance or protective coatings, exposure steadily broke down the structure. The aircraft rested in an unprotected orientation, creating distinct zones of decay. The lower sections of the fuselage, sitting directly in the wet volcanic soil, experienced repeated moisture exposure. This dampness accelerated corrosion across the belly panels and structural rivets. Water entering open compartments could freeze, expand, and work against seams and joints over repeated cycles. The salt-laden air functioned as an electrolyte, expediting breakdown wherever dissimilar metals intersected. Differential survival rates emerged across the airframe based on metal thickness, exposure, and mass. The heavier structural nodes, including the forward crew compartment and the wing center section, retained enough strength to be considered for recovery. Conversely, thinner skins and the rear assemblies were far less complete. The tail section lacked enough surviving material to be rebuilt as an intact section of the aircraft, leaving parts of the rear airframe as a fragmentary record rather than a recoverable structure. Before formal recovery, however, the site condition still needed qualification. There is evidence that at least one small artifact may have been removed before the formal recovery, so the site cannot be described as untouched. But no large recovery altered the main wreckage field before the Aerospace Heritage Foundation of Utah reached it. Once located decades later, how would recovery engineers decide if this specific airframe was the one to pull from the Aleutians? 2 heavy bomber wrecks existed within the target search zone, but extraction engineers could only commit operational resources to one. In 1994, the Aerospace Heritage Foundation of Utah scouted the Aleutian island chain to locate a viable consolidated airframe for long-term preservation. Multiple targets turned the mission into a logistical site selection problem. Historic value mattered only if the artifact could physically be extracted from a subarctic environment. The Foundation initially evaluated a different bomber wreck located 30 miles south of the primary staging facilities at Adak. While this alternative airframe was a potential candidate, the surrounding terrain severely restricted access. The extraction team possessed a fixed budget and a narrow operational window dictated by the unpredictable Aleutian weather. In this coastal theater, clear skies can deteriorate into violent storms within hours, limiting the safe operating time for any exposed crew. Heavy-lift helicopter operations were financially prohibitive and highly dangerous in the prevailing high-velocity winds. Therefore, the retrieval strategy relied entirely on surface transport. Any selected target had to be accessible by a ground team and close enough to a navigable shoreline to permit loading onto a shallow draft cargo vessel. The alternative site failed the surface access test, presenting impassable topographic barriers that blocked any ground movement of large aluminum sections. Consequently, the search grid shifted to Great Sitkin Island, situated 25 miles northeast of Adak. Surveyors located the specific target airframe exactly 1 mile inland from the coast. That transit over rough volcanic terrain was severe, but it remained within the physical limits of a manual transport operation, allowing the Foundation to discard the inaccessible wreck and commit its resources to the Great Sitkin site. Validating the Great Sitkin location required a thorough structural assessment of the remaining aluminum shell. The inherited condition of the fuselage, stabilized after its initial Tundra deceleration, directly dictated the handling protocols. For recovery purposes, the key finding was contrast. Thin outer skins were compromised, while the heavy core bulkheads remained remarkably solid. Surveyors mapped the primary lifting points and inspected the massive wing center section. The forward crew compartment, originally scaled to accommodate a 9-man flight crew, represented the largest and heaviest module targeted for preservation. The appraisal confirmed that it could withstand the stresses of a ground transit. At the wreck site, the wet volcanic soil, bluff, beach, and dense tundra grass translated the access limit into a tool list. Hand tools, saws, cargo pallets, cables, pulleys, wooden beams, and the pulling force of the men and the landing craft type vessel offshore. The sheer mass of the heavy bomber had to be managed without conventional land-based industrial lifting power. Accepting these geographic and mechanical limitations, project managers defined success as securing the strongest forward airframe sections, with the primary fuselage serving as the stable foundation for future conservation. With the access limits mapped, the engineering challenge shifted from identification to physical execution. How could a small team break down a 4-engine bomber without heavy machinery? In 1995, a 20-man team deployed to turn the manual recovery plan into fieldwork. The unit included volunteer reservists from the 419th Combat Logistics Support Squadron and had to move the airframe across the inherited 1-mile overland distance to the coastal extraction point. Because the intact bomber exceeded human lifting limits on soft terrain, the team abandoned single-piece recovery and reduced the aircraft into weight-limited modules the 20 men could physically manipulate. This was practical field deconstruction rather than a clean factory reversal. Saw cuts, pallets, and section breaks were governed by width, weight, drag, and the need to protect the historically valuable forward fuselage and reusable wing structure. The disassembly sequence followed a strict structural logic. Large sections had to be separated to reduce width, weight, and drag during ground movement. Each required cut was calculated around what the team could move across mud, grass, bluff, and beach, while still preserving the core airframe for restoration. The forward fuselage and wings remained the highest value recovery elements, while the severely degraded tail could no longer provide enough material for a complete reconstruction. The ground transit then began, demanding continuous physical exertion and basic mechanical leverage. The crew utilized ropes, portable hand winches, and customized lifting slings to drag the components over the rough volcanic soil. The transport path offered no flat or stabilized surfaces. Every foot of forward progress ran through dense, wet beach ryegrass and mud pits that threatened to trap the heavy components. That forward section became the decisive hauling problem, requiring the men to pull in unison against the static friction of the tundra. To keep severed lower edges from digging into the soft earth, the crew managed the center of gravity of each piece during movement, rotated the heavy radial engines, and dragged the wing sections linearly to minimize ground friction. The logistics squadron personnel used their cargo handling expertise to keep the historical metal from tearing or buckling as it crossed the uneven topography. This methodical transport sequence converted a static archaeological site into an active material convoy. Over a period of sustained manual labor, the unbolted and cut sections finally reached the rocky shoreline. Reaching the water introduced the next bottleneck. The edge of Great Sitkin Island forced the recovery into a marine cargo problem. The shallow draft vessel offshore had finite deck space, rigid payload limits, and no margin for poorly secured cargo. Loading thousands of pounds of aluminum onto a floating platform shifted the boat's center of gravity, so each component had to be placed for stability before the ocean transit. The team functioned as loadmasters, classifying each extracted piece by its structural value versus its geometric footprint. Sections of the aft fuselage that had lost their structural integrity were too fragile and bulky to secure safely for the ocean voyage. The physical transfer from the rocky shoreline to the vessel introduced a hazardous dynamic. The MV Polar Bear, a landing craft-type barge, could not simply sit hard against the shore after striking an underwater rock and springing a leak. It had to anchor about 250 yards offshore. The recovery team bridged that gap by moving parts on cargo pallets, hauling them over the rocky beach with wooden beams, and using fishing buoys washed ashore to help float the loaded pallets out toward the vessel. Every movement was timed against the coastal water, the condition of the cargo, and the need to keep each section controlled before it could be secured for transport. The forward fuselage, with its pilot stations and primary architecture, demanded the most deck space and the strongest rigging. Once it was secured, any remaining capacity had to favor structurally useful material over fragile, bulky aft sections. During the final loading phase, the team prioritized rebuildable airframe structure over symbolic display pieces. The unrestored artifacts displayed beside the aircraft, including a Pratt and Whitney R-183O radial engine, and the recovered tail turret, preserve corrosion, deformation, and environmental damage as interpretation pieces rather than blending them into the restored skin. Available accounts state that the aircraft was disassembled, moved to shore, loaded in pieces, and transported for restoration, with the wings joining the fuselage in Utah years later. They do not prove that other engines or wing material were abandoned at Great Sitkin simply to make room for the fuselage. With the recovered sections transported off the island, the field recovery phase concluded. The targeted structure was safe, yet the original airframe remained incomplete. The surviving Great Sitkin tail could not rebuild the rear geometry alone. The display aircraft therefore presents a strict physical contradiction: authentic B-24D, forward fuselage and wings, completed by a related naval donor without dissolving the identity of the Aleutian wreck. Donor airframe integration is used when major sections of a primary artifact are unrecoverable or destroyed by the environment. Rather than fabricate every missing rear section from scratch, restorers splice in compatible structure whose geometry and load paths can support the primary artifact. To complete the Aleutian bomber, restorer Ed Coletta used the rear fuselage section of a naval patrol derivative known as the PB-4Y-2 privateer. Identified by Bureau No. 5, 9932, this donor aircraft was derived from the B-24 family but was not identical to a B-24D. The privateer had significant design changes, including a stretched fuselage and a single vertical tail. Its relationship to the Liberator made the donor useful for structural completion. The engineering crew placed both sections on specialized alignment jigs to precisely match their horizontal center lines. Splicing two massive 50-year-old aluminum structures requires absolute leveling to ensure the aircraft does not twist or progressively sag once the support jigs are removed. The technicians mapped the original factory rivet lines and aligned the heavy upper and lower longerons. They riveted the overlapping skin panels and bolted the internal support ribs together. The splice created a continuous load path from the original nose compartment to the donor tail, preventing twist across the join and restoring the aircraft's complete static footprint. The restoration deliberately preserved the authentic Aleutian metal of the forward crew compartment while relying on the donor section strictly for structural completion. All exposed metal surfaces were cleaned, treated with modern corrosion inhibitors, and sealed with primer to stabilize the surviving structure for indoor display. On May 17, 2002, the grafted Liberator and privateer fuselage arrived at the Hill Aerospace Museum in Utah. That was not yet the end of the restoration timeline. The wings did not join the fuselage in Utah until November 2006, and the following month the aircraft was finally reassembled for display, with additional interior restoration continuing inside the museum. Indoors, recovery and restoration resolved into controlled curation, leaving the composite aircraft on its landing gear as a museum exhibit and technical record.